All right, today we're going to talk about determinants. Let's motivate this with a slight geometric example first. So suppose we have a matrix, and we're going to look at the before and after graph. And we're going to look at this unit box. So beforehand, we used to look at the circle, but now we're going to look at this unit box. We want to ask what happens to this unit box after we transform it by a certain matrix. So let's just use a nice simple example. And in this case, this matrix is going to double both sides. It doubles the x coordinate, and it's also going to double the y coordinate. And so now the transformed unit box, which is going to be a parallelogram in general, but in this case, it happens to still be a box. We haven't sheared anything or rotated anything. So in this case, we still get a box, but because we stretch it times 2 to begin with in both directions, the area is actually going to multiply by 4. And so what this indicates is we're going to say the determinant of A, or at least the absolute value of it, is going to be equal to 4 because the area of this particular matrix multiplied by 4 under the transformation. All right, so now you might ask, okay, why do we care about this? And the reason we're going to care about this is this gives us a magical tool, in some sense, a magical algebraic tool to compute various aspects of matrices without resorting to row reduction. So for example, let's do another example. Let's look at the matrix 1, -1, -1, 1. And we're going to look at what happens here. So we're going to take this same unit box and see what happens. And this particular matrix is going to have a reduction in dimension. So what's going to happen is that we're going to end up with these two vectors. And so the unit box is now squished. In fact, there's no area here. There's no area whatsoever. So the determinant of this matrix is going to be 0. And this is going to strongly indicate many, many things. So this is going to indicate that this matrix is not invertible. In fact, there's a reduction, there's a squash in dimension. So that's indicative that the matrix is not invertible. And this is also indicative that the columns themselves are not independent. So in fact, these rules hold in general for any matrix A, and this is why we care about the determinant. If the determinant is going to be 0, that means the before and after graph is going to give you some squash in dimension, a reduction in dimension. That means that that matrix is not going to be invertible, and also that means that those columns are not linearly independent. All right, so what's the formula? Let's just jump right to the formula. So we have a 2x2 formula. We're going to keep going up in dimension. So let's start with the easy case. The 2x2 formula should be very familiar. So if you take the determinant of A, B, C, and D, you get AD minus BC. So this should be very familiar. This is in the inverse formula that we know for 2x2 matrices. But I want to point out that this formula algebraically is very consistent with the geometry. So if we look at what happens when you take the unit box right here, and if we map this over by A, B, C, D, in general, we're going to get a parallelogram. For the sake of this example, we're going to assume that A, B, C, and D are all positive. So you're going to get a parallelogram that looks kind of like this. And this is going to be the shape that we want. But now we want to, how do we compute that shape? Okay, so with the formula, according to the formula, it should just be AD minus BC. But why is that? Well, we can look at this length right here. That's just going to be A. This is going to be C. And on the upper side, we're going to get the same thing here. And likewise, the heights are going to be B and D. And here we have the same things, but reversed. And now we can look at various triangles and rectangles. So here we have two rectangles. Right, so those rectangles are BC. So those, we have two BCs. And then we're going to have two of these little triangles here. So we have 2 times 1/2 AB. And then also we're going to have these triangles right here. I made that one a little too big. And that's going to give us 2 times 1/2 CD. And the whole thing on the whole square right here, the whole square is going to be A plus C times B plus D. And if we subtract off everything else, we're going to get what's left is just the blue part, just that parallelogram. So if we expand this out, we get AB minus AD, plus BC plus CD. We're going to subtract 2BC. We're going to subtract those purple triangles, which is AB, and we're going to subtract CD. And sure enough, what happens when we're done? So this BC is going to cancel one of those minuses. The CD is going to cancel over here, and the AB is going to cancel here. And what's left is exactly the area of that parallelogram. So the area of the parallelogram is equal to AD minus BC. And so that's why the determinant of a 2x2 is AD minus BC. All right, so let's just do some examples that we did before. So we're going to apply this formula just with some quick examples. So let's just do the ones we did before. So the example we did before was 2, 2, 0, 2. So that's going to be 2 times 2 minus 0 times 0. That's 4, just like we did before. Just like the geometric intuition, the area of the unit box increases by a factor of 4, and that's exactly what the determinant says. Oops, this is the determinant. All right, and we can do a determinant of this other guy. And this is going to be 1 times 1 minus 1 times -1. And that equals 0. So this is indicative. This right here is indicative that, in fact, 1, 1, and 1 minus 1 and -1, 1, those two columns are linearly dependent, meaning in this case, they're going to be multiples of each other. And then what's great about this is that even when you can't spot it directly, the determinant of something like this, right, when it's not as clear that they're multiples of each other, it also still pans out. This is 1 times 3 minus -3 times -1, which is 3 minus 3, which is 0. So this also tells us that these two columns are linearly dependent and that that matrix is not invertible. All right, so that's what it is for 2x2. Now we're going to go to a 3x3. This is where things get a little more complicated. So let's look at just a nice before and after picture here. So if we take kind of the unit box, so now we're looking at 3 dimensions. So we're going to take the unit vector in each of the 3 dimensions, and this is going to create a little box. And we might take a matrix. Let's take just our favorite matrix, just 2s on the diagonal. This is going to stretch each each dimension by a factor of 2. So what happens to this box? So this box is going to stretch by a factor of 2 in the x direction. It's going to stretch by a factor of 2 in the y direction. And it's going to stretch by a factor of 2 in the z direction. And so now the box, even though you only stretch each dimension by a factor of 2, the box itself is going to get larger by a factor of 8. That volume now is times 8 of what we had before. And so the determinant of this guy turns out to be 8. Now it could be minus 8. So the minus just comes into play when you have a certain amount of flips in dimensions. But the key idea is we care about really, is the determinant 0 or not? And if it's not 0, the absolute value is going to indicate how much of a expansion we have in the area or volume or even hypervolume if we get up to higher dimensions. So now what's the formula for this? So the formula becomes a lot more complicated as we go up. So this is probably the first warning to have, is that the determinants seem nice and easy, and an easy way to determine if a matrix is linearly independent or not, or sorry, if it's invertible or not, or if its columns are linearly independent or not. But as a warning, and we're going to see this next time, the warning is that the formula gets very complicated beyond 3 by 3. Right? So beforehand, we had two terms, AD minus BC. For this case, we have the determinant of AB, oops, that's not a B, BC, GH, and I. What we're going to do is we're going to add up 3 terms, and we're going to subtract 3 terms. All right, so just every determinant, we're going to be multiplying more and more things together and adding and subtracting more terms. So where does this come from? So there's one way of doing this is to just expand just duplicate the first columns. And then the positive diagonals here give you the terms that you're going to add. And the reverse diagonals are also going to be the ones you're going to subtract. So these are all the ones you subtract. And kind of those other one, the forward diagonals are the ones that you're going to add. All right, so that's one way of doing this. Another way of doing this, another way of writing the determinant, is you can write this as A times the determinant of the smaller matrix, of one of a smaller matrix. So you can view this as A, and the terms that you're adding and subtracting with A happen to coincide exactly with that matrix. And then we can subtract, and this is where things get a little weird. We're going to alternate. So B times the determinant of DFGI. So where does that come into play? There's B and there's DGFI. So you'll notice that you're kind of excluding the columns of B. We subtract here because you're in the next column. You're going to alternate in this case. And then plus C times the determinant of DE times GH. So this is another way of doing it. And we're going to generalize this method later. But this is just another way of calculating the determinant, of kind of memorizing the formula. And this is reducing it down to the 2 by 2 case. All right, so let's put this formula in action. Let's compute the determinant of the first example we did with just the cube. So we know the answer is 8, or at least it's plus or minus 8, but let's figure out what it is. So let's use the first method of just doing diagonals. So I'm just going to duplicate the first columns. The first two. And we're going to add these columns right here. And this one should be somewhat straightforward because almost all of these are going to be 0. So we're going to add 8 plus 0 plus 0. And then we're going to subtract these columns. And every one of those has a 0 in it. So we're going to multiply those up. So you get -0, -0, and -0. And sure enough, we get that this, in fact, is 8. All right. So just a reminder, what does this mean? Okay, this means a couple of things. The reason we care about the determinant is it tells us, because that's not 0, that tells us that this matrix right here doesn't squash in a dimension, which means it's invertible. And this also tells us, and this probably is a little more obvious just from eyeballing it, but we know that in fact, these vectors are linearly independent. So that's why we care about the determinant and why we calculated it. We can do another example. So we're going to do the determinant of a matrix. That's a little harder to just eyeball. So here we have this guy right here. All right, and what we care about is we want to know, is this invertible? So normally, to check if it's invertible, you would row reduce it. You have to go through the painful process of row reducing it, finding the pivots, and so forth. And maybe we want to see, is it even invertible before we even try that? Or we want to check, are these columns independent? So if we're asked, are these columns independent, we can just take the determinant and do it that way and just get a yes or no answer. So let's go ahead and do this. Let's do this the other way. So we're going to use the expansion method. So this is going to be equal to 1 times the determinant of 2, 4, minus 2, and 0. So just for emphasis, we got that from there's the minus, there's the 1, and that's the 2 minus 2, 0, and 4. We're going to subtract -1 times the determinant of -1, -2, 1, and 4. So those came from those entries right there. And then we're going to add back 3 times the determinant of -1, 2, 1, and 0. And that came from those guys. All right, so with this one we have so here we have 1 times 8 minus 0. Over here, we're going to subtract -1 times -4 plus 2. And then the last one, we're going to add back in 3 times 0 minus 2. And when everything's said and done, we have 8. This is -2, -1, minus. This is -2. And this here is -6. And we get 0. All right, so this says the determinant is 0. So if we look at the before and after graph, this is telling us it's going to get squashed. We're losing at least one of the dimensions. And in particular, this tells us that this matrix right here tells us that this matrix 1 minus 1, 3 is not invertible. And it also tells us that because we had a 0, this also tells us that these columns are not linearly independent. All right, just as a word of warning, there are a couple warnings to have about this. So warning number one is that the determinant does not tell you how the vectors are independent. So for example, if you want a certificate that two vectors are, that a set of vectors are linearly dependent, you want to express one as a multiple of another or one as a combination of the other, but the determinant doesn't do that. It doesn't give you the linear combination. Another word of warning is that this formula, the first formula we had, this one is probably easier for 3x3s, but it does not generalize. So this formula, the other warning is don't get too comfortable with this formula. You can use it, but just know that this formula right here does not generalize to 4x4 or higher. Right, we're going to be doing higher ones later, but just know that you can't just do these nice simple diagonals for 4x4. You have to do more than that.